All right, welcome. Today we're going to talk about what we've done in terms of the counting here at Devoxx. But we'll first start with who are we, right? I am Kasper Cools. This is Stefaan Haspeslagh. We're both lecturers in computer science. And besides that, we started a company together with Stefaan named encountr.ai. But let's start with the demo, maybe.
Yeah. Okay. We have prepared a demo, kind of the hello world for deep learning. We used the MNIST dataset to train a neural network to recognize digits. But the thing we are doing now today is we are running this deep neural network on the Raspberry Pi. So we are using a neural compute USB stick to be able to leverage this computing power on the Raspberry Pi. So we have a camera, we have the Raspberry Pi, we have the stick on it. Okay, and so when you slide the sheet under it, it recognizes the 5. Even if you are writing not that good like my 5, it will still be able to recognize it.
All right, and just to make sure that we're not fooling you, does anyone want to come ahead and actually try to write something down? Right, Matthias? Yeah. So it doesn't really matter, just pick a number between 0 and 9, or 0 and 10.
Okay, let's see what he's telling about.
And as you can see, we have the fact that it says that it's a 3 and it's somewhat a 70-ish percentage.
You see in the right black box, you see how the neural network is seeing the 3. So it can be mixed up with a 9 sometimes. That's why it's doubting, and we have an accuracy of only 70%. If you have slightly better written numbers, then you have an increased accuracy. So okay. So now Kasper is going to tell you something more about our counting application, about why we are using the Movidius, why we are using the Raspberry Pi, and so on.
Okay, so maybe we should start with what we've done here at Devoxx. Some of you might have seen the keynote, and in the keynote we had Stefaan talking about last year's and what he had done or had to do to actually know how many people are in the rooms. The problem was that you had to run from room to room and check every single time how many people were actually in it. Certain speakers were quite obvious, like Venkat. I mean, everybody knows that the rooms are full. But other speakers, well, we don't really know how the topic is actually doing and how interested people are in those topics. So the idea was, why can't we do something with AI instead of the solutions that we've already tried? Because he has tried some things, but none of them really had a solid solution. So what we've done is, with data flow from Google, we actually created a dashboard, and we used cameras to count all the people here. This is a slide from earlier this morning. So this is a dashboard that we actually created, which shows the percentages of people inside rooms. And this gives us the opportunity to actually create extensive analysis and check and see how the crowd flows are. So we are actually encountr.ai since, well, yesterday actually. So what we do is we count about everything. Right now we counted you guys coming in here, but what we can do is count anything from people to boxes to cars to whatever you think of. And looking at how we can provide those solutions, some of you asked us yesterday, well, why don't you just count the heads? You have models using OpenCV and HAR models, which actually provide the opportunity to count heads. But the problem there is that they don't provide a solid solution. The solution that you create with HAR models is based on one certain point in time at which you create that model manually. So that means if someone has a slightly different sized head, you might not really recognize it. So that brings us to the other part as well. We said that we were able to count lots of objects, right? So using HAR models, we would have to create one model per object that we want to count. So that doesn't work as well. What is the solution then? Well, obviously, AI is the solution to go for. What we can do is create neural networks and use those to detect any kind of object that we want. It gives us the opportunity to create one network that can count different types of models, and we don't have to change them over time. But that brings us to something else. We talked about the Raspberry Pi, and we talked about the fact that we can detect numbers. But how does a Raspberry Pi work? With that Movidia stick, we solved something at which I'm actually coming back later on, because we have 8 rooms, right? 8 rooms means 8 different cameras that detect live images, or actually stream live images, and all those images have to be processed. If you think about one image, that's about 416 by 416 pixels, which means that if we send one image, we have about 9 megabytes of data. Taking into account that we have about a frame rate of, let's say, 20 frames per second, that's quite hard to actually send all that data over a network. So we need to find a solution to actually have all those IoT devices process the images locally and not send them to the server. Thinking about what we have these days, we have all sorts of smart devices. So we're talking about the actual counting of people using images, but we have Nest, Amazon Echo, all sorts of things that we connect to the network, so that creates a large overload. Looking at how many devices we'll have in the next couple of years, the last few years we had a doubling of those amounts. So we had 4.6 billion in 2016, and we expect to have 20.4 billion in 2019. So that means that we can't really keep up sending all that data. That would be just too much. If we would have, let's say, 20,000 cameras running day in, day out, it would be just quite an overhead to send all that data. Thinking about those devices, if you look at the charts of smartphones that you use, 10 years ago, the number of, or the actual data that you sent from one point to another was quite limited. Today we use gigabytes of data to actually perform lots of tasks that we consider default. We connect to Facebook, we connect to all those different kinds of apps. So we need to take that into account as well, because those add a lot of overhead to the network. Why is this actually important? Because I'm not talking about counting, right? The fact is, cloud is dead, long live the cloud. And why is that? Well, thinking about the processing of neural nets, especially when you think about image classification, we have to find solutions to actually provide analysis on a local basis. So thinking about the Raspberry Pi, we don't want to send those frames over the network to another location. We want to process them on the device itself. And to do so, well, first of all, you need some kind of neural net, right? You need to have a set of data that defines, for example, what a person is. What we did last year is we had some footage that was taken here, and we made an analysis on that data. We captured about 1,000 images, I think, and all those images together, we annotated them, we defined what the persons were, and then what he had to actually detect. And then afterwards, we created a basic model. So for those of you who haven't really created a neural net before, basically what you do is you have like 1,000 images to have a basic test case. So if you want to start doing data science with classification and neural nets, think about 1,000 images, and then you can actually get going. One of the first things that we actually had issues with is the fact that when we started, we were actually quite new to TensorFlow and then image classification in general. And what we did was we had some kind of basic model that was pre-trained for us. You could use Inception version 3 or whatever kind of net that you find online. And what we did was we started training our own data set. And what I'm coming to is that if you do this, try to train only the classifying layers and try not to touch the features that were trained before. So don't touch the inner layers unless you actually know what you're doing. So what you do is basically you scrape off the first or the top layer that does the classification, and then you retrain that with your own classifiers, and then you have a model that is workable and that you can actually use. In terms of how to define that model and how to actually go about annotating and then which functions you can actually use, we want to refer to the talks that are actually given here at Devoxx this week. So the one from Janus Bress, Martin had one last year about deep learning as well, which is a very good one. And we had guys from TomTom today as well. So they give you a perfect overview of how you would go about to create your own neural net. But what we want to focus on today is not the creation of the net itself, but the actual running of that net on a device that has maybe no internet connection, or a limited connection in a remote area, or in this case, if you think about the images that we take here from you guys coming into rooms, we want to obviously make sure that they don't really leave the device. Because if we do so, in Europe we have an issue with GDPR. So think about all those things. We really want to have this on a local machine. So last year we had something like, okay, we need to have a solution that's running on one single device. And that device has to be connected to the internet, but we don't want to send too much data over that network because of the fact that, well, all of you guys are here, there's about 3,500 people, and we're all sending data over that network. So what we did was we started trying out some networks. We started with TensorFlow, we started with Tiano, and we tried a few things. And what we noticed was, well, if you are new to deep learning and new to these frameworks, that, well, you run into some issues. A Raspberry Pi is an RM device. That means that you have to look into which drivers are actually available for your particular hardware, and you need to know what is used underneath. For instance, you have an implementation of NVIDIA that provides the ability to connect to the GPU and actually perform logic. You have availabilities for AMD and so on and so on. And the problem is that you need to know what your network actually supports before you run it on that device. So those are the things that we encountered. And furthermore, once you've created that, deploying might be an issue as well. But we'll get into that later on. So thinking about those frameworks, this is an overview of, for instance, what you can use when you have a particular, for instance, TensorFlow. You see CUDA is set to yes and HIP is set to no. If you don't know what HIP is actually from AMD. So if you want to have that AMD, if you have a hardware device that actually has AMD units on it, then you can't really use TensorFlow. So those are the things that you encounter when you try to run those models on hardware that you don't really know what the software needs to use. So those are the things that we actually encountered. Stefaan will now show you how we actually created this Movidius Raspberry Pi solution. So I'll pass the floor to him.
Thank you. So I will just go into the details. It seems rather straightforward to put in the network on this Raspberry Pi and just run it, but there are some pretty important decisions that you have to take. So I just want to give you an insight in the entire workflow, starting from the training of the network until the deployment on the actual device. Because during the entire chain, you have to take some measure into account so you can really run your network that you are training on your device. Those are the problems that we encountered during the last couple of months as well. So I'm using the Raspberry Pi 3B+. It has USB 3 0.0 support. We have the video stick, which is compatible with the Raspberry Pi. We are using a Raspberry Pi camera, and we still need a computer, and we still need some GPU hardware to train our network. So we can't really do everything on our Movidius stick. So the general workflow with the Movidius neural compute SDK is as following. So you first train your network. You do it on your own hardware. We used our own GPU, a pretty good one. Then you will try to profile your network on your Movidius stick. You will see if the Movidius stick has sufficient power to use your network. You can go through your network layer by layer to see which are the bottlenecks in your deep learning network. This really can be a solution. If you have a pretty heavy network with respect to resources, well, then you just use the profiling toolkit of the Movidius stick, and then you can just try to discard some layers. This really can work. So when you have profiled your network, you know which layers are okay on the stick and which layers are not okay. You fine-tune your network, and then you deploy it to your network. Okay, this is an image of the Movidius stick, how its internal workings are. So first you have an application processor, you have the NC SDK, and which has two parts. You have the compiler to transform your original network into a Movidius network, and you have the NC API. Then you can use Python or C++ to access the Movidius stick. And we used Python in this particular setup. Below you see you have a number of sheaves. The sheaves in the Movidius sticks are the computing units. The more computing units you are using, the more power you are using. So it's not a good idea to just say, okay, I will use them all, because if your Raspberry Pi is not connected to, if it is connected to a battery pack, then you have to be very careful not to use too much power, and then you should use less sheaves. Using more sheaves or less sheaves doesn't have anything to do with the accuracy of your network. So you will obtain the same accuracy if you use one or if you use all of them. It's just about using the correct amount of power. Okay. So this is the general workflow we are using. I will show you some Keras code to train our network, just to show that we can use anything if we are careful. Then we will convert our Keras model to a TensorFlow model. Then we will look if our TensorFlow model can be run on the Movidius stick using the NC SDK. And then for deployment, we will use the Movidius stick and the Raspberry Pi. So, first step, preparing the Keras model and preparing the TensorFlow graph. So this is just some normal Python code. When you train a deep neural network, you have to feed it some batches of images. You will not feed your network images one by one, but you will group them in batches. For Keras, the default size is 128 batches. You say how many classes you want to train. We have 10 digits, 0 to 9, so we have 10 classes. And the number of epochs is the number of training rounds that you want to do on your GPU. More information about this, Kasper already told it. Just look at the other talks we have on Devoxx, and then you will know what's there. Then we have to do some transformation. On line 19, I'm just importing the MNIST dataset Keras is giving you. I was kind of lazy for this talk. Keras is providing you with sufficient training data and test data, so you can just import it and use that. So this is what I did. Then you have to convert the images. Neural network is always counting with numbers between -1 and 1 or between 0 and 1. Images are mostly RGB or BGR images, so you have to convert them. This is a very important step. You will need to know the details about the input layer of your neural network. You have to be very careful, and you have to tell to the Movidius SDK what the format of the input tensor is. It's very easy to make mistakes there. So it's very good that you have insight into the training of the network and into the structure of the network. Otherwise, it will be very difficult to deploy it to Movidius. Okay. This is not working. Okay. So then I'm constructing my neural network, line 42 until line 52. It's Keras. I'm using the Keras framework. Then I compile my network. I do a fit of my network. So I'm looking about. I'm training it, and then I'm evaluating it to see if the accuracy is sufficient. And then I just in the last 3 lines I write my code to some graph file on my computer. You can put everything in one Python script. You don't have to really write the Keras file model to a file and then to import it again in TensorFlow. Especially for this simple setup, this would be okay. But if you have larger projects like we have, then it's better to just do things one by one. Okay, this is how I convert my Keras model to TensorFlow. It's just basically an import. Then I will freeze my network. This is a very important step. You have to freeze your network in TensorFlow. Freezing just means that okay, you have in a deep learning network, you have a lot of variables when you are training your network. When you make an inference, those variables do not need to be variables anymore. It should be converted to constants. You really need to do this step, the freezing of the network. Otherwise, the inference is taking a lot more time. So this was an issue we encountered in the early days. We forgot about freezing the model. We just converted it, and we had a very, very slow model. And just by freezing it, using the right tools, then we had a major speed up. Okay. So now we are here. We have the Keras model. We have the tensor graph. And now we have to convert the TensorFlow graph to the Movidius graph. And this is actually a very important step. You cannot just import it. You have to do some checking. I have a screenshot of this here. So you really need to use the checking tool of the Movidius stick. What you are doing there is you are running a sample batch on the native TensorFlow or Caffe background, and you do the same with the same input on the Movidius stick. And you have to compare if those results from the native network are more or less the same of the results of the Movidius one. In some networks, you have a downscaling from floating point 32 to floating point 16, which is used with version 1 of the SDK. It is being solved in version 2, but version 2 is not complete yet. So if you are using version 1 of the Movidius SDK, every floating point is downscaled to a floating point 16, so you are losing accuracy. And when you are doing that, you have to be really sure that your accuracy is still within acceptable boundaries. Otherwise, your results on your Movidius stick will be totally bad. And we had the same issue. So you have the top 5 results that you can compare. So you already see. The first one is the result of the Movidius one. The second one is the expected result, and you see a little difference. It's always the case. You will have differences. In the bottom, you have 5 checks. I will not go into details into what measure is telling what, because then I have to go into details about deep neural networks. You just need to have 5 passes. If you don't have 5 passes, then situation is bad. The threshold is there because of the floating point downscaling. So if you have, for the first one, 2% off, then it's still acceptable and you can still use your network on the movie stick. Okay. So, second one, after you have done the checking, you will do the compilation. Compilation is rather straightforward. You just tell what kind of TensorFlow model you want to use. You will need to have the exact names of the input and the output layer. So you will need to use some tooling to figure this out. This can be really hard when you are reusing existing networks to figure out which input layer is actually used, because sometimes you have multiple input layers, multiple output layers. So you have to really figure out which one that you need to use. With the -s there, you are telling how many shapes that you are using, and you are writing it to a file. And as you can see, the only thing that the compiling tool is checking is if the network can be compiled. It doesn't do any accuracy checks. So if you forget to use the checking tool, then you're in a bad shape. This is one of the errors we made. We just said, okay, we want to try it. We want to do some quick development. We will just compile it and see what happens. And no, nothing happened. Okay, last step. So we have the Keras model. We have the TensorFlow model. We have compiled it into a model fit for the Movidius. And now we have to do the deployment. So now we want to load the graph into our Movidius device. And this is the code that you need to do this. I wrote a simple class for that. On line 8, you see that we enumerate all devices. This is because you can use multiple Movidius sticks on one device. So if you want to do really heavy things like face recognition, which has really very heavy neural networks, then you can just use 4, 5, 6 Movidius sticks to increase the computing power. Of course, this will cost more energy, so you have to really make a trade-off there. In line 13, I'm just using the first stick because I only have one stick, and then I load the graph into the Movidius stick. On line 26, you will see that I am allocating some queues. So the Movidius is working in a kind of first in, first out fashion. You can feed batches of questions, of inferences to the network. This is the num parameter that you can use, but it's always first in, first out. So it's not because you are feeding 5 or 10 images at once, they will still be processed one by one by the Movidius stick. It can be very convenient to use batches because of asynchronous. You can inference your results asynchronously. In this talk, I'm doing it in a synchronous way. I will just wait for my result. But in general, this is a bad idea. So you have the 2 queues, and you just have to pull. You have to look at the different queues. Okay. Now I'm only loading one graph in this example. Every graph needs to have its name, which you can see in line 25. But it's also possible to put multiple graphs on one. Starting from SDK number 2, you can put multiple graphs into one Movidius device. So if you have 2 lower weight deep learning networks, then you can just put more than one on one stick. Okay. So, and the last step is just to feed some image to the network. You put it into the memory, which is basically putting it into the queue. Then the microprocessor will see that something is in the queue. It will take the question out of it, and it will make an inference. And for the number of 6, because we are using a softmax layer, you will see that the sixth element is 1 in this one. So we have predicted a number 6. This is very simple. You just use the graph that you have loaded in a couple of slides before. You put it into the FIFO queue, and you just wait for the result on line 37. Okay. And I'm just using the inference labels, but normally you have the inference probability as well if you want to use them. And very important, after you have finished your work, you have to clean things up. So you have to destroy your queues, you have to destroy your graph, and you have to close your devices to clean up your resources. This is very important. If you're just pulling the plug, you don't have to care. But if you want to reuse all resources on your device, you should do your proper cleanup, or things will go badly. Okay, so we walked through every different component of our setup. We can create a model, we can convert a model, we can check if the model is fit for the video stick, we can deploy it, and we can make inference. And we just wrapped everything into one application, the one that you saw in the demo. We use OpenCV to take the images. We wrote an image converter, very important because, okay, like I told, the image is not the input format that the network is expecting, so you have to do the conversion. I left the details out of this presentation. You have to initialize the video stick. You have to trigger the camera. And then you wrap the important parts within some kind of while loop. I'm continuously pulling, looking at images. So in 76, I'm just preparing the image, which is actually preparing the input tensor, which is a regular NumPy array. In line 70, I do the inference. And then I just show you the result. Okay. So, are there questions? Yeah.
In the end, you're counting people, right? How does that work?
Okay. So we are counting people in the end. It's basically the same workflow. So we took a lot of images. The important thing here was that we had to train our network. Most networks are detecting people in front, but we are detecting them from top on. So this was the first thing we had to tackle. So we had to train this network. And then we used some special tricks. So we are using frame by frame, and then we have to look at the flows. We can't go, because we are a company, we can't go into particular details how we did the actual tricks. So
yeah, but maybe just in addition, the reason why we showed you the video stick is because this was the most important part in creating this solution, right? All the other things like counting people from above and then counting the heads. As we mentioned, you can find great talks on Devoxx editions, like Martin's talk about Mints last year, the guys from TomTom, and they tell you how to build those networks. But the problems that we faced were actually more on a local basis, as in how will we process all that data on Raspberry Pi? And the solution that we found was the video stick. So that's why we're not really telling you how to count people, but telling you how to do that on a mobile device, because that was the main issue that we actually faced. Yeah.
In the stand-up, or the keynote, you mentioned you were having some issues, and I was thinking about it. Have you thought about using multiple input devices, so you have like people walk on it, it gives you inputs, and then you do a voting system?
So
You have one device, so that's visual taking a picture.
Yeah.
You could have some other kind of input.
oh, like multiple devices sharing data.
Yeah, and then
Yeah.
they all vote and say, okay, that's a person.
That would be doable, but then again, think about what we want to do as a company. We want to be able to count almost everything. So that's why we don't want to include too many sensors, because thinking about a mobile setup, especially things like Devoxx and events in general, we don't want to have 15 different kind of sensors measuring all that stuff. So we want to have one compact mobile thing. So we could do that, but AI is definitely smart enough. Deep learning networks can effectively do what we want to do. The only thing that you have to take into account is that you have to have enough data to train it. So those are the issues that we have today. The fact that we haven't trained that many data sets. I mean, we actually don't have enough info to process all that info. Okay. Any other questions?
Do you have any plans for custom boards, or will you continue to use Raspberry Pi with Mobius?
Okay, so do we have any plans to use other boards? Well, absolutely. The reason why we use this is because this is at hand today. So it's actually all the things that we found that we could buy and use immediately. But we definitely will be looking into custom hardware because that's what's actually going to make everything happen, because then you can control the hardware itself if you use Intel or whatever kind of CPU. So yeah, we'll definitely do that.
Yeah. This started as a hobby project. So we looked really into low-cost devices first as kind of proof of concept, and now we know what we need to do. Now we know the load we have. Now we know the particular network we have to train, and now we can look for proper hardware to fit with the problem. So this was a very important step to really know what is the exact problem, and now we can do the matching between the hardware and the problem. So we just used some quick solution, get to know it, get to know the problem, and now we have liftoff.
Yeah, because basically at first we were kind of naive, as in I told you guys that you have to take into account that sending all those images over the network creates a big load. I mean, one image is 9 megabytes. If you take 20 frames per second, that's times 20 every single second for 8 cameras. So that's an enormous amount of data. So those things that we encountered ended up in you can use a video stick, and that's a start for us. So everything else it's important, but you can get that from other talks. So that's why we actually focused on this particular NPU neural processing unit. Any other questions? Okay, yeah.
How much was the stick cost?
The stick itself, the price on it is, I think we paid 60 euros without VAT, VAT. So I think it's about 80, something like that, yeah. It's from Intel, by the way. I forgot to mention. It's an Intel stick, yeah. Okay, great. If there aren't any more questions, thank you. I hope you had something that you can use later on.